So this is the second solution video for E3 Radioactivity Paper 2. The first two problems, numbers 1 and 2, were the first video. Alright. So number 3 says 3a, what's meant by the half-life of a radioactive nuclide? And Mark's scheme says, time for the activity or the number of parent nuclei in a sample to decrease to half of the initial value. It says this question's from a previous syllabus. It may have minor differences in marking or structure. I don't think so. I think this will be in the current nucleus, especially based on the equations that they have. So also, it's not hard to say what half-life is. One thing that they point out is that don't allow the word nuclide. It's nuclei, and nuclide is making reference to the the parent, like actual, say, oxygen, nitrogen, uranium, americium, like those are nuclides. The nuclei inside are not nuclides. So just be careful on the phrasing. All right, so 3b. Yeah, 3b is not too bad anyway. It says the activity decreases to original activity over 8 after a time of 37 years. And then it says calculate the half-life of tritium. Well, a over 8 means that 3 half-lives have already happened. So we have half of a half is a quarter, half of a quarter is an 8. So 3 half-lives have happened. And so 37 years is 3 half-lives. Then the half-life is 37 divided by 3, which is 12.3 years. So that doesn't even need like the half-life formula. And the alternative 2 does work. You say that A equals A naught e to the negative lambda t. We know t and we know a. And so you can figure out the decay constant, and then knowing the decay constant, half-life is the natural log of 2 over the decay constant, which gives you 12.3 years. And so the formulas do work. I think that's way more work than you need, but I guess if you don't really understand half-life, or you don't notice that 1/8 is 3 half-lives, then yes, I suppose the only route to take would be to use the activity equation. Anyway, so deuterium, and then C. So for deuterium, it says we have deuterium plus tritium yields something plus a neutron, and just run the numbers through. So we have X, and on the left side we have 2 plus 3 is 5, and on the right side we have 1, meaning that 4 must be, or X must be 4. Why does my pen look so weird? I'm scratching into the solutions. And then for the proton count, for the Z number, we have 1 plus 1 on the bottom here, and then the neutron has 0, so then I must have 2 in this spot. And what is 4 and 2 but the alpha particle? So that must be the alpha particle that is created, and that's what the Mark scheme says. And so for these nuclides, we have the binding energy per nucleon in mega electron volts for each of these nuclides. We have deuterium, tritium, and X. I wonder if that's alpha. But anyway, so it showed that the energy released in the reaction is about 18 mega electron volts. The reaction is the same reaction as described above. We have deuterium plus tritium yields alpha plus a neutron, plus some energy. Oh, I see why it says X, because they don't want to give away the fact that it's an alpha particle. Very smart. So Mark's scheme says 4 times 7.074 minus 2 by 1.112 minus 3 times 2.827. What's happening is they're actually working starting with the products, and so that alpha particle represents 28.296 mega electron volts of binding energy for the 4 nucleons, and then the hydrogen, the deuterium, and the tritium that fused to make the alpha particle was, throw that together, you get 10.705. So the difference between them, we get 17.591, which when we round becomes roughly 18 mega electron volts. Interestingly, it says in the Mark scheme that the calculation shown should have at least 3 significant figures in order to get the second marking point. which you should follow significant figures anyway, but based on my math, I'm seeing 5 or at least 4. The original numbers had 4 significant figures. So anyway, just don't just write, yeah, 18 seems legit. Show your math so you can get full credit. Right, that's DI. What's DII? DII says estimate the energy in joules released as a result of the fusion of a kilogram of nuclear fuel according to this reaction. And so first of all, the reactants, it says mass of reactants 5 times 1.661 times 10 to the negative 27. So that's the mass of one universal mass unit. And so we have 5 nucleons, the two the 2 nucleons from deuterium and the 3 from hydrogen, from tritium, giving us 5. And then there are 5 times 1.661 times 10 to the negative 27 kilograms, giving us a mass in that reaction of 8.3 times 10 to the negative 27 kilograms. Then when they ask for the energy from 1 kilogram of fuel, we're really looking at joules per kilogram here. And so the energy that we got from the previous problem, it said 17.6 mega electron volts worth of energy that we get out of the reaction. So there's our 17.6 times, right there. There's our 17.6 times 10 to the 6, so it's 17.6 mega electron volts, but that's electron volts. We have to include the electron volt to joule conversion right there, the 1.6 times 10 to the negative 19 joules per electron volt. So now we're in joules, and we say joules per kilogram. Well, the mass in kilograms is right here, the 8.3 times 10 to the negative 27 that we just found. So if we do the 17.6 E6 times 1.6 E negative 19 divided by 8.3 times 8.3 E negative 27, what do we get? But 3.4 times 10 to the 14 joules, which is a solid amount of energy. And then DIII says the specific energy, or the energy density, of typical fossil fuels is about 10 to the 7 joules per kilogram. And what we just figured out is that in a fusion process, that's roughly 3 times 10 to the 14 joules per kilogram. So like 10 to the 14 is 10 to the 7 more than 7 orders of magnitude more than the 10 to the 7. So yeah, that's fusion is 10 million times more powerful than fossil fuels are. Now this is interesting. I mean, I kind of pointed that out, the 10 to the 7 greater, but it seems from the mark scheme that they actually want you to identify the order of magnitude. You just can't say, oh yeah, it's so much bigger. You need to have the quantitative detail. So there you go. All right, pretty cool. That's why they keep on working on fusion reactions. Okay, we're at 8 minutes, so let's go to number 4. Okay, so 4A, quarks. I'm not sure that quarks are part of E3, but anyway, A1 is still a good question. State what is meant by an elementary particle. And this question has been identified as not part of the new syllabus. Well, thank you very much, Question Bank, for including it. I still think you guys should know what an elementary particle is. So, a particle without structure has no other smaller particles. There's nothing else is making it up. You can make arguments about strings and whatnot, but those are not particles in the sense of how we consider a particle. So, without any component particles, elementary particle. Okay, so they're getting into quarks here, and they're talking about like the weak force. This is not, at the very least, this is not E3. So we're going to skip those. But BI is useful, so let's zoom in on that. For BI. By reference to the concept of binding energy, why the combined mass of the nucleons of a nucleus is greater than the mass of the nucleus itself. And I would say because of binding energy, but that's the question. What the heck does that mean? And so we have E equals mc squared. What happens is that, and I like the first answer, it says energy is released when nucleons come together. True. There's that binding energy. And so the nucleus has less mass than the individual nucleons, correct, because the mass that was lost, that missing mass, the mass defect, becomes energy by E equals mc squared. Okay. Right. And so you need to mention the mass defect and the binding energy, but you also need to mention E equals mc squared for the second mark. And, all right, so that was BI. What does BII have to say? So this question is very similar to 3DI. But anyway, we have thorium, radium, and helium, and it says what's the energy released in the decay of thorium into radium and helium when we have the binding energies per nucleon for each of the nuclides, thorium, radium, and helium. So if we look at the mark scheme, it does the math for us. And so breaking this down, we can see the 224 for the radium plus the 4 nucleons for the alpha particle. Those are the products from the reaction, and the reactant from the decay, if you want to call it that, a reactant, for the thorium, you subtract that out. And so the difference between the two sides winds up being 5.520 mega electron volts, which is fine. They also allow a conversion into joules. It did not require joules. Interestingly, they say if you list the answer as negative, you only get one of the 2 marks. So be careful about that. Okay, we have BIII. Says, observe that sometimes alpha decay of thorium is accompanied by gamma ray emission. Suggest an explanation for this observation. Well, gamma ray only happens in one way, and that's when it says the nuclei exist in energy levels, and then if the radium is excited after that exchange, after that reaction, then the radium will lose that excitation by emitting energy, pure energy, massless energy in the form of light or gamma radiation. So the gamma ray emission that happens when an excited nucleus falls to its ground state and emits that energy that it had in the form of the gamma ray. Okay, that was number 4, and we're pushing up on 15 minutes, but we can probably squeeze in 5. Number 5. 5 says that you're going to get fluorine 18 when a proton at high speed can interact with oxygen 18, and it gives the process. It says that oxygen 18 plus a proton yields fluorine 18 plus X. What is X? Again, balance out the numbers. So there are 19 nucleons on the left side, and there are only 18 on the right side. So I need one more nucleon for X. But I have, for the proton count, I have 8 and 1. That gives me 9. So then X is going to be 0 down there. And what would that be but our good old neutron? So X is a neutron. AII, that's an interesting question. Why must the proton be traveling at high speed for the process to occur? The proton is going to be very much repelled by the oxygen nucleus because the oxygen nucleus has 8 protons in there, and so that electrostatic repulsion is going to be intense. And so the nucleus is positive and is going to very positive and is going to repel that proton, but we need to get close to the nucleus. We need a close approach in order for the nuclear force to actually be effective, for the proton to actually have an interaction in that nucleus. So if that is going to happen, you need a high kinetic energy to get me high potential energy. In other words, get close enough to the nucleus to actually have a nuclear strong force effect to overcome the electrostatic repulsion. That's a cool question. I like that question. All right, 5B. And so 5B says fluorine 18 is a positron emitter ejected into a patient during a medical procedure. Initial activity required is 1.5 gigabecquerels. The patient is unsafe to others until this activity has decreased. It says decay constant of fluorine. Remember that is the lambda, right? Lambda for this fluorine 18, is 1.1 times 10 to the negative 4 seconds to the negative 1. Calculate the time taken for the activity to decrease from its initial value of 1.5 gigabecquerels to 1.2 megabecquerels. It also says, assume none of the fluorine leaves the body of the patient during this time. All right, so we're going from 1.5 gigabecquerels to 1.2 megabecquerels. Okay, so we have our starting rate, we have the rate we want to get to, we have the decay constant, and we want to solve for time. So finally, the use of the activity equation that actually makes us solve for time. Okay, so knowing the starting rate, the new rate, the 1.2 times 10 to the 6, the decay constant solving for time is a naught e to the negative lambda t. So I isolate the exponent, I divide both sides by a naught, and then I take the natural log of both sides to get rid of the exponent, and we just have negative lambda t equals the natural log of a over a naught. Throw all my numbers in, solve for t, and I get 64,826 seconds, which matches the mark scheme right here. C, positron can also be produced through the process of pair production. So what's the relationship between particles emitted in pair production? When a pair of particles is produced, if a normal matter particle is produced, you must also produce an antiparticle with it. And it says the other particle produced during the pair production would be an electron. I'm not sure if you guys learned that in HESSEL, that a positron is the antiparticle of the electron. It's an antiparticle. And it said don't allow anti-positron because you can't say anti-anti, right? It's the electron is the normal matter particle. CWS says why pair production can only occur when a single photon is close to a nucleus. Mark scheme says reference to momentum conservation, or the fact that energy momentum cannot be both conserved, or that the nucleus redistributes the momentum. I'm not even really sure what they mean by that. But for C4, it says what is likely to happen out to the positron after its production. It meets the electron and then it annihilates, and it goes right back to being energy, usually in the form of a gamma particle. So there's number 5. I think a bunch of that is not E3, but this part right here with the decay constant and the activity rate is definitely E3. So there's number 5. We are now past 15 minutes, and so I'm going to cut. And so this video will be numbers 3, 4, and 5 from E3. Thank you.